Hello students, in this video we'll show how to compute the curl in orthogonal curvilinear coordinates. Let's be given orthogonal curvilinear coordinates u, v, and w as we typically do. Then of course we have unit tangent vectors in these coordinates. We have I hat, which is partial r partial u over the first Lemay coefficient, j hat, which is partial r partial v over the second Lemay coefficient, and k hat, which is partial r partial w over the third Lemay coefficient. So that's our unit tangent vector basis. And we have this sort of standard cross product relationship between these things. Over here we have I hat, j hat, and k hat. So whenever we cross, we go around this configuration just like I, j, and k. But of course, I, j, and k, these I capital, j capital, and k capital depend on the coordinates u, v, and w. They're not constant, right? So not constant. That's an important distinction here. All right. And so now, of course, let's recall that the gradient of a function f, grad of f, is equal to 1 over h1 partial f partial u h1 I hat plus 1 over h2 partial f partial v j hat plus 1 over h3 partial f partial w k hat. So in particular, what this tells me, if I do the derivative with respect to u, I get the relationship, and for cyclically, that the gradient of just the coordinate u is going to be what? It's going to be 1 over h1 I hat. So I hat over h1. And then similar for grad v and then grad w, right? So grad v is going to be j hat over h2. And then grad w, the coordinate grad w is going to be k hat over h3, okay? Good. And now I need to remember one vector identity for curls, right? Namely, if I want to look at the curl, recall from our previous discussions on vector identities that the curl of fv, for f a scalar, is going to be f, the gradient of f, cross v, plus f, the curl of v. That's a vector identity for curl, right? And so in particular, what can we say? This automatically implies that if I look at the curl of a, and we know that the curl of a gradient is 0, and the curl of gradient g for any g is the 0 vector. Okay, excellent. So with these identities over here, we can find a relationship for curl in orthogonal curvilinear coordinates, right? So let's consider a vector field v, which is vi I hat plus vj j hat plus vk k hat, like so. And I'm going to compute the curl of this first thing over here, right? So let's do the curl, for example, the curl of vi. And now I'm going to replace I hat with what? I'm going to replace I hat with h1 and then grad u. Okay? That's really the curl of v hat I. And so what will this be over here? Well, now, of course, if we do, I'm going to treat this as my function over here, f, and that is my gradient field. So I'm going to have the gradient of this function over here cross the grad of u, and then plus f times the curl of this gradient. But the curl of a gradient is 0. So I'm only going to get this first term over here when I do the curl, right? So let's do that. It's going to be the gradient of vi h1. And then cross the gradient of u. And I'm going to replace the gradient of u now with what it's equal to, which is going to be what? Which is going to be I hat over h1, like that. Excellent. And so now we have to recall what the gradient is. So the gradient is going to be what? Now I'm going to omit the term of the gradient. Gradient's over here, right? So in other words, but when I do I cross I, I'm going to get 0. So I'm going to omit this first term in the gradient in my calculation because it's going to 0 out when I do the cross product. So I'm only going to put the second two terms over here, right? This is going to be 1 over h2, and then d by dv of what? D by dv of vi h1. That's a j hat. And then plus a what? Plus a d by d, a 1 over h3, d by dw of vi h1. That's a k hat. And again, we're going to cross this with I hat over h1, like so. Okay? Great. And so from this, we're going to get two terms. What two terms are we going to get from this? Well, we're going to have a what? We're going to have a negative term because j cross I is negative k. So that's going to be a negative 1 over h1 h2 d by dv of VI H1, and that's a K hat term. And then K cross I is going to be J. So we're going to have a 1 over H1 H3 d by dw VI H1. And that's going to be what? K cross I is equal to J. So that's going to be a J hat component. Great. So I have two terms over here. Let's do the same thing with the VJ H2, right? So let's go to VA. Let's do that now. So let's do VJ H2. So what will the curl of VJ H2? And that's going to be grad V be? Grad V. Well, by the same calculation, it's going to be the gradient of this function over here. This time we're going to omit what? We're going to omit the J term over there because the gradient's going to vanish when I do the cross product over here. So it's going to be 1 over H1, partial U, and then VJ H2, that's going to be an I component, and then I omit the J because it's going to vanish out when I cross product, and then we have a what? Then we're going to have a 1 over H3 d by dw of VJ, and then H2, that's a K component, right? We're going to cross that with J hat over H2. And let's gather the terms and see what we're going to end up with, right? So I'm going to have this first term over here, going to be I cross J is going to give me a J term, so I'm going to have 1 over H1 H2, 1 over H1 H2 d by du of Vj H2, and that's in the direction of what? That's in the direction of K hat, and then a 1 over H3 H2, 1 over H3 H2 d by dw of Vj H2, and what's that going to be? It's going to be a K cross J. K cross J is negative I, so it's going to be a negative, and that's going to be an I hat over there. Okay, we got those terms together. Excellent. Let's do the last terms. So what are the last terms going to be? The last terms are going to be the curl of Vk H3 grad of W, and by similar reasoning, this time we're going to punch out this term because we're going to cross K hat, right? So this is going to be a 1 over, we don't have the K hat term in the gradient, so we have 1 over H1 d by du of Vk H3 I hat plus what? Plus 1 over H2 d by dv of Vk H3, that's going to be a J hat, and we're going to cross that with what? We're going to cross it with K hat over H3, like so. Excellent. Hopefully we're seeing the tenor of this argument now, right? And this is something that's excellent just to replicate by yourself once you go through this derivation, right? And so we're going to have a couple terms over here. So we're going to have a 1 over H1 H3, I cross K is negative J, right? So that's going to give me a negative J, negative 1 over H1 H3, and then d by du of Vk H3. That was an I cross K we found out was what? Was negative J. So that's a J hat. And then we have an H2 H3 plus 1 over H2 H3. D by d what? D by dv, Vk, that's a Vk, and then an H3. And then what's the vector component over here? The vector component is going to be what? I have a J cross K. J cross K is equal to I, right? So let's put this all together. So the conclusion now is what? The conclusion, therefore, is the curl of this vector field V, where of course V is what? Where V is going to be Vi I hat plus Vj, J hat plus Vk, K hat is going to be equal to what? Let's gather the I terms over here. So this term is an I, and then this term over here should be an I with a negative, right? So I'm going to have a 1 over H2 H3, 1 over H2 H3, because both of the I's have an H2 H3, right? And then I have a d by d what? The positive thing is a d by dv of Vk H3 minus d by dw of Vj H2. That's the I component. What's the J component going to be? The J component is a 1 over H1 H3. This is the positive, it's a d by dw, and then a Vi H1, and then a minus d by d what? So I'm looking for the other J over here. The other J is right over where? Negative over here, d by du, Vk H3. Those are my J components. And then finally, what are my K components over here? My K components are going to be plus. The K's are where? So this term is a K, so it's a 1 over H1 H2, 1 over H1 H2. And then this is the first K over here, it's a d by du of Vj H2. And then where's the other k? The other k comes up top over here, right, which is a negative d by dv, and then a what? Then a vi, and then a what? And then an h, then an h1. And these are my k components. And so we have this expression over here for the curl of v in orthogonal curvilinear coordinates, right? So there's my expression for the curl in orthogonal curvilinear coordinates. You might say, is there an easy way to remember this formula other than doing this derivation over here? Well, there's sort of a classic way to do this, right? So what we can do is we can say, of course, this is going to be what? This is going to be the determinant of what? Of I hat. Now, I hat's over what? I hat's over h1, h2, over h2, h3 rather. J hat over what? And j hat's going to be over h1, h3, h1, h3. K hat's going to be over h1, h2. And then I have a partial u, partial v, partial w, right? And let's check to see what work goes over it. So what's the I component going to be? It's going to be the v derivative of what? It's going to be the v derivative minus the w derivative, right? So the v derivative of what? It's the v derivative of h3vk. So I'm going to put an h3vk, an h2 Vj, and an H1 Vi over here, right? And so that's sort of the quick version of how we compute the curl in orthogonal curvilinear coordinates using this sort of this more classical determinant formulation of what the curl is going to be. In particular, in Euclidean coordinates, what do we see? In Euclidean coordinates, all the Lemay coefficients are constant, just 1. And so when the Lemay coefficients are constant, just equal to 1, this is just going to turn to ijk d by dx, d by dy, d by dz of vi, vj, vk, and that gives you the standard definition of curl. So this is the more general definition of curl in terms of these Lemay coefficients, right? So that shows us the power of being able to compute the Lemay coefficients quickly and then employing any one of these theorems for divergence, gradient, or curl, or Laplacian in these orthogonal curvilinear coordinates in order to generate quick expressions to solve boundary value problems or to find angular momentum operators or different differential operators in different coordinate frames. Very useful tool in order to quickly do calculations in terms of separation of variables, solving boundary value problems, all sorts of things that occur in mathematical physics. Thank you very much.